saw something called the fundamental theorem of calculus. Right? Can somebody tell me what that fundamental theorem of calculus did for us? What was so great about the previous fundamental theorem of calculus? Mariah, go ahead.
Sure.
You look like you want to tell me.
I remember it was that you can find the area under a graph. You take the integral of the second endpoint minus the integral of the first, or take the antiderivative of the second endpoint, subtract the first, and that gives you the integral.
That's right. That's right. So you could get so fundamental theorem of calculus II was you can get the definite integral by evaluating the difference, get the definite on AB by evaluating the difference of an antiderivative at the endpoints. Right? And that was great because it allowed you to avoid doing the process of using Riemann sums or right endpoint approximations and taking limits, right? which was awful. Okay, so there's something else that's called fundamental theorem of calculus I. And for most people, I think this is more mysterious, but it's also equally important. And in fact, it's another way of looking at fundamental theorem of calculus II. So previously, we justified the fundamental theorem of calculus II by using the mean value theorem. Right? We said we used the mean value theorem to get this. But in fact, there's another way of getting to it. It's using fundamental theorem of calculus I. So it's a little bit strange, so let me put it up. So let f be continuous on AB. Then the function, let's call it big F, defined by integrating little f from a to x, is differentiable on AB, and f prime of x equals little x. In other words, is an antiderivative of little f. Okay, so roughly speaking, what this says is that one can construct an antiderivative. Right? As long as the function, for continuous functions. For continuous functions, one can always construct an antiderivative. And that antiderivative is something funny. You use it by you make it using the definite integral. Okay. So somebody gives you a function and says, here's my function. What is the antiderivative? Okay. And you say, well, I don't know, but I know that for any continuous function, I can make an antiderivative in the following way. What I do is I'm going to make a new function f, and I'm going to define f. I'm going to make a new function big F. And big F of x is going to be the definite integral from a to x of little f. Okay, so it's sort of like an area function. Okay, so for any x that you give me, then big F will be the area from a to x. Big F is going to be the area from a to x. Okay, and this area function guy turns out to be differentiable and an antiderivative of the original guy.
But x is arbitrary?
Yeah, x is your variable. So you're integrating from a to x as x. So suppose somebody gave you some function from 0 to 1, from 0 to 10, say, here's your guy, right? If you wanted big F of 5, that would be this area, right? This would be big F of 5 because it's the integral from 0 to 5. Okay. Okay. So this area guy, you make up this area guy, and then you do it. Okay. And it turns out that this thing is the antiderivative. Okay. So this thing is an antiderivative. So. Okay, so let's think about this thing. So why does this happen? Why is this an antiderivative of little f? Why is this an antiderivative of little f? Okay, so I'd like you to think about it for 1 minute. I'd like you to think about it for 1 minute and see if you can figure out some reason why big F prime of x equals little f of x. Right? Why is big F prime of x little f of x? Or just maybe think about what big F prime is. Okay. Actually, that's what I want you to think about. So think for 1 minute. What is big F prime anyway at x? Okay, turn to someone next to you and say, I've forgotten what the derivative is. Is that true? No. Or something you would not say. You might talk with Megan. Say. Okay, so what is the derivative of a function? What's the derivative of a function? Can anybody remember the derivative of a function? Kimai. Slope of the tangent line, right? So how do you get that? Is the limit of
f of x minus f
of h is equal to 0. Okay, so let's think about that. Well, what is that? What is f of x? Let's just expand this out. We're subtracting off f of x. F of x is the integral from a to x of f. Right? Big F of x plus h, what's that?
Why are we using the capital F this time?
Because we're taking the derivative of it, right? We're differentiating capital F.
Oh.
We want to show that this guy's derivative equals fx.
Oh, okay.
That's what we're hoping. Okay. Well, what's big F? Big F of x, right? That's the integral from a to x. Big F of x plus h, what's that?
to the integral of a to x.
The integral from a to x plus h. Right? And we're dividing everything by h, right? Okay. Okay. Can anybody simplify this a little further? The integral from a to x plus h minus the integral from a to x.
Oh, does this go back to the basic properties of
Yes, it does. Yes, it does.
That being said, though, I don't know which one of those would.
That's good. I mean, that's not good. That's not good. But even so, you know what it's related to, right? So the neurons are firing.
Yes.
Right? The neurons are firing. The synapses are firing. Something is firing. Yeah, Victor.
So when you take away the integral from a to x from a to x plus h, you're just left from a to from h to x. Is that correct?
Nope. You're going from we've got the integral from a to x plus h, right? We subtract out the integral from a to x, and we're left with the integral between
X to x.
and x plus h. Yeah, fine.
How come you can't just like eliminate and then be 0?
How come you?
Because it'd be like h plus h when h goes to 0 will equal x.
Yes.
And so it'll be the integral of x of a to x of f minus the integral of a to x of f.
Well, it would be like 0 over 0.
That's the same thing. It's a 0 over 0 sort of thing, right? Like you could
Oh,
say,
yeah.
right?
Okay.
You have to take the limit, right,
Yeah.
and see what happens in the limit. Yeah. Okay, so we get from x to x plus h, f, and divide the whole thing by h as h goes to 0. Okay. The limit as h goes to 0, the limit as h goes to 0 of 1 over h times x, the integral of little f from x to x plus h. Okay. Right, so here's x plus h, right? Right, and we have this is the integral from x to x plus h over f, right? That's this area here. Okay. Now what happens if where is h in this picture?
It's the distance between one and the other.
It's the length of the width of the base, right? It's the width of the base. Right. Okay. So what does this thing mean here? You can figure this one out. I'll be very impressed. I'll give you a 1 point on the bonuses on the 1 point bonus on the final. What does this thing mean? If you take this area here and divide by h on the bottom. Think for 30 seconds or a minute or so. Megan, do you have an idea? Yeah.
You get like the height of the x equals to x, you get the y value?
You get the what y
The
value?
average value?
The average y value. Very good. Okay. The average y value. Great. You get the point because you twitched. Okay. So right, you get the average. What you get is the height of a box. Right? You get the height of the box with the same area. Right? This, if I take a box with this height, this box has the same area as this thing here. So it's an average. What it gives you is the average height, the average value of f. Right? This thing here is the average value of f on the integral. Right? Does that make sense to people? Right? You get this average. You get the average. You divide. You get a box. You get a box of constant. If you draw something like this, the box of constant height. Then it has the same area. So it's sort of like you've smoothed it out. You've changed everything to water and let it settle. Right? You let it settle, and it settles to an average height. Okay. Okay. So now what we're doing is taking the limit. If we let h go to 0, then what happens to that? As h goes to 0, we're going to get the average value of average value of f over this interval, 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 over smaller and smaller intervals, right? We get the average height. What does that average height tend to as the interval gets smaller and smaller?
Next.
What does that average height tend to? What's the average height over as we let smaller and smaller intervals occur? Good.
Yeah.
Yes, it is f of x, right? F of x. Right, so it'll tend to f of x. Right. Everyone see that? Right. You have this thing, maybe it wobbles around a lot, right? Maybe it wobbles around a lot. X plus h, right? So over here, you get some, the averages are changing, but as you get closer and closer, as you take smaller and smaller intervals, right, then the average value is going to get closer and closer to just f of x itself because of the continuity of your function, because of continuity. So this is really because f is continuous. Okay. And that's why this guy is an antiderivative, right? So you get f prime, you make this area function guy, and then you look at its derivative, and lo and behold, its derivative is little f. Okay, so you've created an antiderivative. That's the moral here. Given any continuous function, you can actually create an antiderivative. Okay. Yeah, Mariah.
Wait, I still don't understand how we create the antiderivative.
This is it right here. We make it.
But like how do you, like if you're given any function, like how do you just come up with an antiderivative?
So I guess what you're asking is like, how would you actually do this practically?
Yeah.
Right? Like if somebody gave you some crazy function, would you be able to? It wouldn't be so simple. You'd be able to sort of like get a rough idea of what it was, right? I guess you could use a computer to get some idea of what it was, right? You could get numerical estimates of what it was.
Okay.
And that's about as good as you can get. But the importance of this is sort of more the fact that you can create an antiderivative at all. It's sort of like a theoretical achievement rather than something that you're going to actually do. Okay, so yeah, you wouldn't say, oh, here's my crazy function. Now I've got the antiderivative. Okay, this is not that useful an antiderivative, although it will be useful later if you take differential equations. Okay, so, but this is more like something useful theoretically, for now at least. Okay, so I hope, anyway, the main point is this, that if you have any continuous function, then this area guy turns out to be the antiderivative. Okay. If you have any continuous function, you make this area guy, its derivative is your original function. Clear?
How is that different than the first, or the second fundamental theorem of calculus?
The second fundamental theorem of calculus is talking about evaluating definite integrals using any antiderivative. This one is about creating a specific antiderivative.
Okay.
So you can create a specific antiderivative. Okay. Let me try to show you how we get how this fact implies the second fact. How this fact implies the second fact. Okay. So let f be continuous on AB. Okay. Let G be any antiderivative of f. let big F be the antiderivative we just constructed. We just made. Right? The integral of little f from a to x. Okay. Well, what we're hoping that the definite integral of little f equals the difference of g of b minus g of a. Right? That's what we're hoping to show. We actually know that already, but pretend that you've forgotten why it's true, and we'll see in another way why it's true. So I'm just going to ask you questions, as I usually do. Let's see. So these guys are both antiderivatives of f, right? G and big F. Big G and big F, they're both antiderivatives of little f. Should I slow down? Maybe I'll stop a second. Everyone all right? Okay. So big G and big F are both antiderivatives of f. What can you tell me about them? They're both antiderivatives of the same function. Then, go ahead, Claire.
They must differ by c.
They differ by a constant, right? So, right, we know that big G equals big F plus some constant. Right? They have the same derivatives, they must differ by a constant. Okay. You say, okay. So, well, big G minus big G of B minus big G of A, that's going to be f of b plus the constant minus f of a plus the constant. Right? So what's the punchline? Can anyone jump to it?
The constants like cancel.
Constants cancel, and? Kelly?
G of b minus g of a equals f of b minus f of a.
Yes? Right. So you get f of b minus f of a. But we're hoping, remember what we're hoping that that's going to be the definite integral from a to b, Sarah?
Well, can't you just substitute g of x into so because f of b plus f of c equals g of b because of what you just said down there.
Are you going to make me go back to g from here? I don't want to go back to g.
Oh, you don't. Okay.
No, because we started from g. We're leaving it.
Oh, okay.
Okay. Anyone say the punchline? Yep, Mariah?
Maybe not.
Go ahead.
Well, I mean, it does not prove then that the b to a, integral b to a to f equals g of b minus g of a, because f of b minus f of a equals that, right?
Yeah, let's take a look. So what's f of b? F of b is the integral from a to b of
f.
Little f.
Yeah. So
And what's f of a?
A to, oh wait, no.
A to A.
A to a of little
Yeah.
f.
Yeah.
And what's that?
It's just
That's zero. Not zero. So that's it. Any other antiderivative differs from the area guy by a constant. And for the area guy, f of b minus f of a is the definite integral from a to b. So the definite integral from a to b equals the difference of any antiderivative at the endpoints. Okay.
Why do we use g instead of f for that one?
G is, remember what the fundamental theorem of calculus II says. It says you can take any antiderivative, evaluate at the endpoints, and get the definite integral.
Okay.
Okay. So here it is. We take any antiderivative, and lo and behold, we see that we get the definite integral. And so this is another way, sort of avoiding the mean value theorem, although secretly no. sort of avoiding the mean value, seeming to avoid the mean value theorem, that you can see the second fundamental theorem of calculus. Okay. So this is another way of saying it. Okay. Any questions about this? Any questions? Emma, do you have a question? No?
Wait, isn't this like almost exactly like the mean value theorem?
It's kind of similar to the mean. There's actually a mean value theorem hidden inside here. And further, it uses a lot of the mean value theorem. For example, here, how did we get this fact? The mean value theorem. Right. Right. So we cannot really avoid the mean value theorem. The mean value theorem is actually like the secret hands behind everything. Okay. Okay. Any other less perceptive questions? No. Any other questions? Okay. So what is this? So right, you can always create an antiderivative, and so this allows you to do sort of a little bit strange. It also allows you to do kind of strange things. So if I say, what's the integral? If I have something like this, right? I make a function. So exercise. I make a function, and I say, what's the derivative? What's the derivative of this? Okay, it looks pretty awful, right? You might think maybe I have to integrate this thing first, figure out what it is in terms of x, and then differentiate that thing back, right? Oh, sorry, going too fast.
Wait, sorry, the function on top is the Wait, what's the function on top?
F of x is the integral from a to x of this function here.
Okay, so f of x is the antiderivative, and
Yeah.
that's the original function.
So now I'm differentiating it,
Okay.
and what am I going to get? I'm going to get back the.
Yeah.
Go
Go ahead.
ahead.
You get back the original one.
You get back the original function. So you get back the original function. Okay. You don't have to say like integrate this thing and then differentiate it again, which would be a pain and impossible for you at this point. Okay. Okay. So right, you just say, oh look, this is one of those area guys, right? This is one of those area guys for this function, and so when I differentiate it, I'm just going to get back that function. Okay. Right. Similarly, right, if I said something like right, d to the t squared dt, a to x, and I wanted you to differentiate that. You say exactly the same thing. This is one of those area guys. I'm differentiating it. Right. The function here is the integral from a to x of this original function. So when I differentiate it, what do I get back?
You do the x.
E to the x squared. Right. I get back my original function.
What do you put on the other side of the equal sign?
This.
Just that as this.
This equals this. Right. So I'm just doing the same thing as up here, but more concisely. I could say let big F of x equal this thing, then f prime of x equals this thing, right? But just in one move, we can write this more concisely. Okay. Okay. Now for a tricky one. Tricky one? I know. Okay, and this is, I guess, maybe the last thing I'll show you. Okay. So, suppose I want to differentiate something like this. Looks even more awful, but you know that this is something.
Wait, is that a t or an x?
This is an x.
Okay. Oh wait, in the
Okay.
radical.
And here these are t's.
Okay.
Okay, who wants to say something? So 3 people have indicated. 4 people? Okay. I'll go first.
Okay, the square root of 1 minus sine square of x.
Square root of 1 minus sine squared x. Okay. Kimai?
Is that cosine?
Cosine x?
No, it's, well, it's
Just
like,
just
it's
cosine
not-
of x? Oh, is
Yeah,
this
yeah.
cosine of x?
That's cosine.
This would be cosine of x. Or it'd be actually line of cosine of x. Gwen?
That's what I was gonna say too.
Okay. Okay. Megan? That's what you were going to say? Okay. So let's see what this is. So let me sort of break it down. You've got f of x. Let me write it like this. Okay. Okay. If let this be this, then my function here I'm going to write as f of sine x. Right? This is f evaluated at sine x. Right? If I make the area guy, and then this is a composition of the area guy with the sine function. Okay. Okay. So what's that when you differentiate this? Right? So if I differentiate that, what am I going to get? Anyone see?
Is there chain rule?
For the chain rule, I'm going to get f prime. Oops. F prime sine x times cosine x. Okay, so not exactly what people were guessing. You guys were close, but missed one factor. So what you get is going to be little f at sine of x times cosine x. Right? In other words, you get the square root of 1 minus sine squared x, which is good, and then times cosine x by the chain rule. So use the chain rule. So the thing to do is just recognize that the chain rule is involved here. Right? If I had done, say, this, suppose I put in cosine x there. Well, then what's the answer? Kelly?
Square root of 1 minus cosine squared times negative sine squared.
Negative sine x. Right. Again, you've got a composition of this area guy with the cosine function. So you take the derivative of the area guy, that's just the integrand, right, evaluated at cosine x. So you get the integrand evaluated at cosine x minus the derivative of cosine. Times the derivative of cosine. Right.
Yeah. Well, I'm kind of confused about A. So if it's from A to sine x.
Yeah.
Wait, I don't really understand what happens to the A.
A is just a constant. Right?
Okay.
It was A. So A has to be some constant. Maybe it would have been better if I didn't say 0 here.
Okay. Yeah.
Is that better? But A is just some some fixed number.
Okay.
Yeah, I didn't specify what A was, so you're right to be like, what is A? Who is A? You didn't tell me. Okay, that's it. So that's it. Bye. Okay, so that's the end of the course. I hope you learned something and enjoyed it, and maybe got to see that math is kind of interesting. You can actually talk about it and explore ideas. Math is really something about ideas. Quite, yes.